Okay, it's 8:20. So let's start with announcements. And I do have several of them. So first announcement, I have finished grading the quiz. I have uploaded that graded quiz to Blackboard, as well as my solution. So as always, you are urged to check out the solution. I will say, I would appreciate if everybody looked at the way I did the very first part of the quiz, the first question. Almost nobody did it the way with the care that I wanted to see. Okay, almost nobody. So check out that solution, especially the very first step. I want us to be able to start the way I set it up on the quiz, E mechanical 1 equals E mechanical 2. Start at that point logically and go logically step by step instead of jumping to over about 2 or 3 steps and then just writing something. Okay, so I want everybody to check that out, please. This is a usual week for 110C, so we have homework tonight, we have homework Thursday night, and we'll most likely have a quiz on Friday. This is not a usual week for 110L, as I have been saying, right? This is the lab exam week. So make sure to, as you're scheduling your time for the week, schedule, set aside up to 8 hours. I don't think it will take you 8 hours, but that's how much time you have. It is now available, the exam, and the absolute latest you can turn it in is Thursday, this Thursday at 11:59 p.m. Okay. You find it on Blackboard. You do all your work by yourself, as I have said. Please watch my video if you haven't yet about the rules and the procedures. And then you submit to Blackboard all your work in a single PDF file. Okay. Next week, lab will be back to its normal procedure with a new experiment. Okay. Question over here.
Sorry, from reading the outline for the lab exam, it looks like we can't talk about it like even after everyone's finished.
That is correct.
So, like, next week, we still can't.
Correct.
Okay.
No talking to anybody in perpetuity, because we use these exams in other contexts, in other situations. Okay, so just go ahead and store that factoid in your brain that you're not allowed to talk to anybody even after you've turned it in. Okay. Okay. Now, one more thing. Those of you who are first-year students, remember to be talking with your academic advisor, because Thursday morning is when you get to register for classes for next semester. You have to talk with your advisor first so that your advisor can click a button that authorizes you to register for Thursday morning. And advisors are not supposed to authorize advisees if they have not met with them beforehand. As you're thinking about next semester, let me give you one piece of information about Physics 111, the next course for this sequence. It came to my attention just yesterday afternoon during advising that what self-service says for the timing of Physics 111C is not what we had intended. At one point, I had said that Physics 111C is going to be at the same time as 110C, same time block. Monday, Wednesday, Friday, 8:20 to 9:10 in the morning, just like this semester. So I was surprised when I saw on self-service yesterday afternoon that that's not what the time says. It says something like 10:30 to 11:20 or something like that, or 10:40 to 11:30 or something like that. It's not what we intended. So I'm sorry if anybody's already scheduled, but I think that's going to change. So if you have already done the scheduling, hopefully you still have the 8:20 time slot open.
I do have it open. I noticed that for all of the STEM classes, I know that some of them.
Yeah, I don't know what has happened. Yeah,
Okay.
unfortunate.
Okay, I just wanted.
Yeah. So the plan is, it hasn't happened yet, that it'll be at 8:20, Monday, Wednesday, Friday. Yeah, I'm hoping. But I'm not the one who actually makes the change. So it's out of my direct control. But I have the powers that be working on it. Okay. Yeah, I agree. I would like to have it ready, changed so that you can do your scheduling without having to worry about anything. Okay. So you already have something in the 8:20 time slot you're looking at?
No, I'm thinking to change one of my one that is for the 10:30 to 11.
Right. So if we get it all corrected, then self-service will be happy. You'll have no problem. That's my preferred outcome, that it get changed today. So just stay tuned. It'll just show up on self-service as a new time once they do it. But I don't know exactly when they're going to do it. So I am sorry about that. And I think there's more than one situation, like Colin is referring to, where I don't think those times are all right. Yeah. And I know that's a headache. And at least I noticed it before first year students have to register. So hopefully we can get it corrected. Okay. Okay. That's all I have for announcements. Let
Do we
me,
have actual labs
Oh.
today since the
No,
lab
we do
exam is
not.
this week?
we
Thank
do
you.
not. Mhm. Does anybody see? Here it is, my projector control. Okay. That's right. No lab today. No actual lab meeting in the room. You're working on your lab exam on your own. Okay. Okay. So we have one more topic in chapter 11, as I mentioned at the end of class on Friday, and it's our third conservation law. So I have kind of hit some of the key, and yes, I've written these in out of order on purpose, some of the key learning objectives from actually chapter 11, section 7, and then there's the learning objective for section 8. But I wanted to emphasize two key things from chapter 11, section 7. Okay, in this order. One is, what do we do in the situation where we have an extended body? You can't treat it as a particle, and it's rotating about some axis of rotation. So I've drawn a kind of a blob shape, just because I wanted to have some kind of generic shape. Some kind of solid blob that we have put an axis through. I have chosen it to be the z-axis, and we're rotating the thing about it with some angular velocity omega. What's the formula for the angular momentum of that thing? Angular momentum. Remember, we have a formula for angular momentum of a particle, r cross p, where r points from the point you're calculating the angular momentum about out to the particle. And as the particle moves, that r vector follows it. That's for a particle. But I'm talking about an extended body, something you can't treat as a particle, like a rod that's rotating about an axis of one place or another. All right, this is the formula. Now, technically, we're only going to be finding a component of the angular momentum of this extended body, namely that component along the axis that the thing's rotating about, which in this case I've called z. The symbol for the angular momentum of an extended body is a capital L, because it's a total angular momentum of a system. Think of the extended body as a whole bunch of particles. And this is the total angular momentum, z component, for this system of many particles to make up that extended body. But the formula is very simple. The z component of the total angular momentum of that extended body is just two things multiplied together. The rotational inertia of the extended body about that axis of rotation times whatever the angular velocity is. This you can think of as the rotational analog to P equals mv. Because that's what it is analogous to. But it's L equals I omega for an extended body. Okay? All right. Now, another learning objective or thing that we have to understand. What is the Newton's second law we need to use if we want to study something like that? An extended body that's rotating. What's the appropriate version of Newton's second law for an extended body rotating about an axis? Here it is. Remember the symbol there is a tau, which is the symbol for torque, which is a vector. What do? You take the total torque, but only from external forces. All right, so we call those external torques. You take the total of all the external torques, and if there is a net external torque on the body, then its total angular momentum will change. And in fact, the net external torque on the body will equal the rate of change of its total angular momentum. This is just like the version we saw for a particle. Tau net equals d little l dt. Remember, little l is the symbol for the angular momentum of just a particle. Although we have to add external here in a system, because with a system with many particles, there can be internal forces from the particles on each other. But what Newton teaches us is any torques that they might produce, which would be internal torques, occur in pairs, Newton's third law, and they cancel each other. And so it's only external torques from external forces acting on the thing that can change the angular momentum. Now that leads us to the last learning objective for this chapter. Here, chapter 11, section 8, the one and only learning objective for that section. And it is just this result right here in a special case, which I'm going to now write here. When no external net torque acts on a system along a specified axis, no net external torque, tau net external 0. If that's true, then Newton tells us immediately that d capital L arrow dt equals 0. The rate of change of the total angular momentum must equal 0. But then that means if the rate of change of something is 0, then the something is constant. In this case, capital L. Okay. So if you have a system where there's no net external torque, then the angular momentum of that system cannot change. And you can get all kinds of very interesting phenomena from this fact. Things that you can observe in nature, things that I showed you in the video lecture for today in some videos. I showed you the video lecture of the professor on the rotating stool, holding out two little barbells, started out with an initial angular velocity of rotation, pulled the barbells in, and then rotated much more quickly, and then took them back out again and didn't rotate quickly. And we argued that that's a conservation of angular momentum problem. And when the person brings the barbells in, guess what happens? That part right there gets smaller. Rotational inertia depends on the mass and how far it is from the axis of rotation. So when you hold these dumbbells and you bring them in like this, you've brought the mass closer to the axis of rotation. That makes the rotational inertia smaller. That part gets smaller. But if that thing has to be constant and that gets smaller, then that has to get bigger. So the consequence is the person rotates, spins faster. It's the same effect with ice skating. Yes, we've all seen ice skaters do a spin with their arms out. and then bring their arms in, and they spin very fast. And then they take them back out again, and they don't. Or I talked about the case of the person diving off a diving board and how they can adjust their angular velocity of rotation about an axis through their center of mass by adjusting their shape, i.e. changing their eye. Okay. And then I showed you a video that we made in the department of me holding the spinning bicycle wheel while standing on a turntable. And initially the bicycle wheel was rotating clockwise as I looked at it, and then I just turned it over so that it was rotating counterclockwise. And then I was on a turntable, rotated clockwise because the whole system had to conserve angular momentum. So there are actually quite a few situations in the real world where you see this at play. And so what I want to do for the rest of class is I want to do some Wiley plus problems that involve conservation of angular momentum. So please note the technical reason that angular momentum for a system is conserved is if the net external torque is 0 on that system. That's the technical reason. As far as chapter 11, section 8 is concerned, some of the times, in some of the problems, not all, but in some, we're going to have collisions. We're going to be back to collisions again. Things colliding. But what's going to be different now compared to chapter 9 is it's going to be collision coupled with rotation. And if you have colliding bodies that are rotating, what your brain wants to go to is conservation of angular momentum. So let me show you the first one. We're going to have two disks collide. All right, I'll read it to you. We'll get some of the important information. Then I'm going to have to raise the screen so I have some board space. Here's the wording. We are in some kind of a situation, it says here it's an assembly line, in which we have a large uniform disk rotating counterclockwise when viewed from above with an angular speed omega sub capital D absolute value of 1 radian per second about an axis through its center of mass and perpendicular to the flat surface of the disk. That's this one. Okay? It's a disk, which means it's a much more symmetric shape than that. And it's rotating about this dashed axis here. Counterclockwise when viewed from above, there's its angular velocity, omega sub big D, 1 radian per second. There's a second uniform disk with the same mass as the first disk, but half the radius. It rotates clockwise when viewed from above with an angular speed omega little d absolute value of 3 radians per second about an axis through its center of mass and perpendicular to the flat surface of the disk. That's this one. Smaller disk, bigger disk, smaller disk. It's rotating clockwise. See how the curved arrow is going? With an angular velocity omega little d. So we've got omega big D and omega little d. And they're in opposite directions. Okay? All right. Initially, the second disk is suspended just above the first disk, with the center of the second disk displaced from the center of the first disk by an amount equal to half the radius of the first disk. In other words, just like you see right there. Suddenly, the second disk is allowed to fall onto the first. And the two disks undergo a completely inelastic collision in which they move with a common angular velocity after the collision. What is that angular velocity? Okay? So this is the rotational version of a completely inelastic collision. This is one rotational version of a completely inelastic collision. Let me get myself some appropriate working space here. And this is our first example. The colliding disks. All right, we had the initial picture, but I'll draw it again. I'm going to draw my pictures as top views, okay? We're looking down from above. We've got the big disk, the axis of rotation, and then my top view is coming right out at us. This disk has a radius big R. Let's say, by the way, that the axis coming straight out of the board towards us is the plus Z axis. And it has an angular velocity that is counterclockwise. So I'll draw that like that. Omega sub big D of 1 radian per second. All right, now in this top view, I'm not gonna be able to show you the gap, but there's a little bit of a gap, and then hovering above, suspended above the big disk, is the smaller disk. Like that. That's supposed to be a nice big disk, a nice small disk, I should say. With a radius R/2. There's its axis, okay? Still coming out of the board towards you, so still, the axis is still plus Z direction. But this disk is rotating clockwise with an angular velocity omega little d. Okay? Clockwise, by the way, means negative angular velocity. Remember chapter 10? It's -3 then, radians per second. Okay, that's initial. That's picture 1. Before the collision. Okay? All right, now let's draw picture 2. Picture 2 is going to be just after the collision. Now the collision is going to be just when the two make contact. And yes, there's probably going to be some kind of complicated slipping and messiness going on during the actual collision of the spinning disks. I don't care about all that. Once the collision is over, what I've got is a picture like this. Big disk, axis of rotation, and then sitting in the same location is the small one. But now there's only one axis right here, okay? And the whole thing then, this is just now sitting on top of that. You see what I'm saying? Because it's a completely inelastic collision in which they rotate with the same final angular velocity. I'll call it omega 2. About that axis. But the question is, what is that omega 2? For one thing, I don't even know which way this thing's going to spin, right? Because beforehand, this thing, the big one was spinning counterclockwise and the little one was spinning clockwise. So it's kind of anybody's guess afterwards which way this composite thing is going to spin. So I'll just draw arrows like that and call that omega 2. It said, look, it's either counterclockwise or clockwise. I'm going to have to figure out which way. Okay? All right, now whenever you have a collision, you take your system to be the things that collide. So the two disks. Okay? And yes, there's big internal torques when they're come into contact with each other for a while. But internal torques can't change the angular momentum. What we have is a collision of rotating bodies. So we're going to use conservation of angular momentum. The angular momentum about the z-axis in picture 1 must equal the angular momentum about the z-axis in picture 2. Just before the collision, just after the collision. Now I start writing down what I can about each of those things. Okay? All right. So before the collision, picture 1. What can we say about L1z, the angular momentum of what you see right here? Okay, Well, what I've got is two spinning disks. The disks are extended bodies. So I have to use this formula right here for angular momentum. Rotational inertia times angular velocity. Okay, with appropriate plus or minus sign depending upon the sign of that omega. So the question is, what do I write? Well, for the big disk, let's write that as I big D and omega big D multiplied together. That's for the big disk. Where that's got to be the rotational inertia of the big disk about that axis right there. That's what it's rotating about. Plus, well, now we need to be careful. I little d times omega little d. That's technically the way I would write it. Everybody understand the notation so far? Now be careful about this notation and make sure we're clear on what they mean. This is the rotational inertia of the little disk about its axis of rotation, which of course is right in its center. It's still z, but it's about there. That's where it's spinning before the collision, about that axis. And this is technically correct, but now what I'm going to do is a couple of things. First thing I'll do is remind myself that that angular velocity right there for the little disk before the collision is a negative quantity because the little disk is rotating clockwise before the collision. I don't want to lose track of that negative sign, so I'm going to write the second term like this: minus I little d times the absolute value of omega little d. Make the negative value explicit so that I can see it. Question.
Does the blue disk below this, if it stops spinning, hit the other disk?
Yes, there will be some slipping and messiness, but once the collision is over in a fraction of a second, it will just be riding on top of that. Okay. Now, what can we say about these I's that I see? I big D and I little d. Let's say something about each of those. Rotational inertia about the given axis of rotation for whatever object I have. This is the big disk first, I big D. That's the big one. All right, this is a standard shape, and it said it's a uniform disk. That means its mass is spread out uniformly. Its axis is going right through its center this way, which is its center of mass. So we get to go to that table in chapter 10 and look up the rotational inertia for an axis through the center of mass of a disk going this way. And it's a very simple formula. It's 1/2 the total mass of the disk, I'll just call that big M, times the radius of the disk squared. I've already called that radius big R. That's all there is to say about I sub big D. Now let's say what we can about I sub little d. Now I'm talking about the rotational inertia of the smaller disk, about its axis of rotation, but that's also through its center of mass. So it's the same basic formula, 1/2 times the mass times the radius squared. But use the symbols correctly, 1/2. Now, one bit of good news, we're told the smaller disk has the same mass as the bigger one. Must be made of some different material. Doesn't matter. That's what they tell me. So use the same M. But the radius is clearly different. You got to put in the correct radius using the notation we have. The radius is big R over 2. That whole thing gets squared. Squaring things, by the way, folks, is something we've got to practice a little bit more at being careful about. A lot of times I see on the quizzes squares being dropped. Okay? You just got to go very methodically and very slowly and carefully. Note then, R over 2 squared means that 2 is squared downstairs. That's a 4. There's already a 2 downstairs. That means what this really is 1/8 mr squared. Okay, now, when I get ready to start doing more substituting, I'll just put these expressions in. That will go where I big D is, And that expression will go where I little d is. Okay? All right, now I'm going to go on and write down some stuff about after the collision. Oh, let me start higher up. That is to say, what can I write down about L2z? The angular momentum from this picture. All right? All right, be clear. The axis of rotation is now here. That is the only axis of rotation there is. And the little disk is just sitting on top of the big disk as that whole thing rotates. But it's still an extended body. So the formula for the angular momentum will be the total rotational inertia of that thing times whatever that angular velocity is. So let's write that as I total times omega 2. Still that formula, you just have to write it down in a way that is applicable to this picture too. And now we got to spend some time talking about I total. What can we say about the rotational inertia of this whole thing? This picture. Okay? Well, just think of it as two subparts combined. The big disk with the small disk riding on top of the big disk with the small disk center located right there. Okay? All right. Well, first of all, part of this is still the big disk rotating about its axis through the center, yes? So that contribution to I total has not changed. But there's also a contribution from the little disk that's just sitting and riding on the big disk. I'm going to call that now I little d prime. That just means it's different now than it was in the first picture. Okay? So the prime just means it's a new value for I little d. And we got to figure out what to write about that. Well, what I've got when it comes to the little disk is I've got this solid body rotating about this axis. Note then the axis of rotation for the little disk is not through its center of mass. It's displaced over here to here by an amount that's exactly big R over 2. So now we have to go back into our memories into chapter 10, where we learned about rotational inertia and how to calculate it, and figure out how to get the rotational inertia for that disk, but not for an axis there, but there. The idea that we would want to come to your mind is what's called the parallel axis theorem, which I said in chapter 10 is going to be important. Because here it is again, I need it. It says, take the rotational inertia for an axis through the center of mass. That was what I was calling I little d, and I've already figured that out. Plus, because now the axis is shifted away from the center of mass, plus the total mass of the thing times what the book calls h squared. What is h? H is the distance you shifted the axis from the center of mass. So we started with the axis through here, and we've shifted it over to there. So the h is big R over 2. That's what's going to go in for the h. Let's see what we get. ID prime. Okay, the ID that I had already is the rotational inertia for an axis through the center of mass. I had 1/8 mr squared, plus the added part that makes the rotational inertia bigger because we shifted the axis away from the center of mass. M times h squared. H, remember, is R over 2. So you got to square the R over 2. Again, we got to be careful with the squaring. So what is this? Well, it's 1/8 mr squared plus, what do we have here? 1/4 mr squared. The next thing a physicist would do is look at that and say, I can combine those. You can factor the mr squared, and then you have 1/8 plus 1/4. Adding fractions. That's 1/8 plus 2/8, that's 3/8. So the final result for the rotational inertia of the little disk when the axis is over here at this point is 3/8 mr squared. So notice then what I total is. It's I big D, okay, we already worked that out, 1/2 mr squared plus I little d prime, 3/8 mr squared. This is from the big disk, that is from the small disk. But again, the physicist would look at that and say, oh, I can simplify that. Factor an mr squared, and you have 1/2 plus 3/8. So again, I have two fractions to add. That's 4/8 plus 3/8. That's 7/8 mr squared. Okay, so now I should be in a good position for taking the symbolic expressions L1z and L2z and setting them equal, requiring that the total angular momentum before the collision equals the total angular momentum after. Okay, look over here. Don't lose track of where we did the earlier work. Here's L1z. Let's go ahead and put in the I big D and the I little d. So we have 1/2 mr squared times omega big D minus 1/8 mr squared absolute value of omega little d. That's L1z. L2z is I total times omega 2, and there's I total. 7/8 mr squared, and multiply that by omega 2. Again, the physicist looks at that and says, let me simplify that. On the left, I'm going to factor a 1/2 mr squared. That'll leave me with, inside the parentheses, omega big D minus absolute value of omega little d over 4, close parentheses. And on the other side, I have 7/8 mr squared omega 2. Now look, there's an m on both sides, cancel out. I do not need to know the mass of those disks. There's an r squared on both sides, cancel that out. I do not need to know big R. Let me multiply both sides by 8/7. If you want to, you can simplify things this way. Bop, bop, 4. Remember, our job is to find omega 2. So just solve for omega 2. That means multiply by 4 and divide by 7. 4/7 times omega d minus absolute value of omega little d over 4. My inclination is to write this as 1/7 and then distribute the 4 through. 4 times omega big D minus the absolute value of omega little d. And that's what I would call the symbolic answer, because it's written in terms of the things that I was told in the problem. Now I plug in, and I've been very careful with plus and minus signs to account for the direction of the angular momentum. So whatever sign I get out for omega 2, that'll tell me which way the thing is rotating. Positive sign means counterclockwise rotation. Negative sign means clockwise. For the omega big D, you enter 1 radian per second. For the absolute value of omega little d, you enter 3 radians per second. I can see it's all going to boil down to the sign of the number inside the parentheses. 4 times omega big D minus omega little d. And that's 4, and that's 3. That's going to be a positive number. 4 minus 3 is 1. It's 1/7. of a radian per second. And that number turns out to be, so this is omega 2, positive 0.143 radian per second. And the positive sign is telling you that it's counterclockwise rotation. So it's going that way. Here's something I get out of this, by the way, out of this symbolic answer. I can tell you more than just this. What I'm going to have for omega 2 for these particular omega big D and omega little d. I can tell you a lot more. I can tell you from this that if the absolute value of omega little d is exactly equal to 4 times omega big D, that thing in there will be 0. Right? And that means omega 2 will be 0. So after the collision, no rotation at all. If that's equal to 4 times omega big D. Because in that particular situation, I have just as much positive angular momentum as negative before the collision. And the result afterwards will be no rotation at all. Now in our problem, omega little d was less than 4 times omega big D, and we had counterclockwise rotation. But what if omega little d, absolute value, had been larger than 4 times omega big D? Then that thing in the parentheses would be a negative number. And that would mean the whole thing would be rotating clockwise afterwards. I can tell you exactly which way it's going to rotate, if at all. And I only need to know 2 values, omega little d and omega big D. Okay? That's a collision with rotation. The conserved quantity is angular momentum. All right, I have about 8 minutes. So what I want to do is just sketch for you how to solve another collision problem with rotation that you've been grappling with for a couple of weeks now, the ballistic pendulum. Okay, with correct physics. So in this problem, let me show you a picture. You'll note it, you'll recognize it right away once I show it to you. Look familiar? Okay. You're firing a bullet into a block on the end of a rod. There's the axis at the top. Your goal is to find out how fast the bullet is going before the collision. The information you're given is mass of the bullet, 1 gram. Mass of that block, 0.5 kilograms. That block is attached to a 0.6 meter rod, non-uniform mass distribution. Non-uniform. That means you can't go to the table in chapter 10 to get the rotational inertia for that rod. All right. The rod has a mass of 0.5 kilograms. We're going to take the system to be block, rod, and bullet, because they're all involved when this collides. Okay. So bullet collides there, just like in the lab, the whole thing rotates about that axis afterwards. The rotational inertia of the rod alone about axis A is given. They didn't have to tell us that because it's not a uniform rod, so that I can't use any of those equations in chapter 10. Okay? And we get to treat the block as a particle, it says. First question is just work out the rotational inertia for this whole big system. Block, rod, and bullet about axis A. Okay? Well, I'll just kind of set it up here. There's the axis it's rotating about. There's the rod. But the good news is we're told the I for that, for axis A. So not a problem. Okay? All right. Then there's the block. So it has a contribution. We'll call it I block. It says I get to treat the block as a particle. You'll want to remember the rotational inertia formula for a particle. It's easy. Take the mass of the particle times the perpendicular distance it is from the axis of rotation squared. This rod has some length L, so this is the mass of the block times L squared, if we get to treat it as a particle. That's its I, about axis A. Likewise, we have the bullet, which is just about to hit the block. So it also contributes, although it turns out it's negligible, but I'll write down the formula for it. Clearly, I would treat the bullet as a particle. That would be mass bullet, how about that? Times perpendicular distance from the axis of rotation squared, so L squared. So all you need is I total then. I rod plus I block plus I bullet. That's I rod plus mass block times L squared plus mass bullet times L squared. And you just plug in the numbers. And the size of that number is quite small compared to those two. But technically I put it there because it should be there. The number I get, 0.24036 to keep extra sig figs. 24036 kilogram meter squared. If I round that to 3 sig figs, 0.240. So now you know the rotational inertia for the whole thing about that axis. Okay? All right, let me get myself some space here. Now the collision happens. Completely inelastic collision. The bullet gets embedded inside that block. So if I think of this as the initial picture, picture 1, that's right before the collision. And the bullet is traveling this way with some velocity VB. It's about to hit the block. Picture 2, the final picture, will be just after the collision, just after. So all I have in that case is a rod and a block and a bullet embedded inside it. And the whole thing is now rotating with some angular velocity omega 2 about A. Take that axis to be out of the board, that is to say plus Z. So we have a collision. So L1Z equals L2Z, a collision with rotation. Now, let me write down what I can about the L2Z first, actually, because it's easy to write down. There's picture 2. I have an extended body. It's got some total rotational inertia, I total, and then I multiply that by that unknown angular velocity, omega 2. I times omega. That's the expression you would use for L2. What about L1? This is one that gives people a little bit more trouble. This picture. There still is angular momentum here, even though you might think that nothing is rotating, but actually something is. The position vector from the axis A out to the bullet is rotating as the bullet travels. So even a particle traveling in a straight line can have angular momentum. But it is a particle, not an extended body, because it's only the bullet that's moving. So go back to R cross P, angular momentum for a particle. And you got to do magnitude and direction. You do the direction with the right-hand rule. The R goes from there to the bullet. The P is the same direction as the V. You should practice the right-hand rule. You should conclude that the angular momentum from the bullet is coming out of the board, plus Z. What about the magnitude? Well, magnitude R, magnitude P, sine phi, or phi is the angle between R and P. But it turns out that magnitude r sine phi is just the perpendicular distance from the axis of rotation to the line of action, as it were, of that linear momentum, right there. So I just take the magnitude of P times that distance, there, right there, which is just L, because remember, the block is to be treated as a particle. So here what you put is mass bullet, V bullet, that's the P magnitude, times the so-called moment arm, L, in the plus Z direction, out of the bore. Now put the L1 and the L2 equal. Mass bullet, V bullet, length L, that's a length L, not an angular momentum, right? That's a length of the rod, equals I total times omega 2. And this problem tells me actually what the omega 2 is. That's the angular velocity after the collision. So in this problem, they told me that. 4.5 radians per second. We've already worked out the I total, and they give me the mass of the block and the length L. So you just solve for the V of the block in terms of what I'm given in this problem, and you get that expression. And there you just plug in numbers. And I will write down what you get. You get 1,800 meters per second. So that's the physics that you needed to analyze our experiment correctly. Now, we didn't have you do all that. We had you do an easier version in the analysis. As you might recall, we had you use conservation of linear momentum in the collision, in which we were cheating and assuming all the mass of the ballistic pendulum was down here, the bottom. Then you can use conservation of linear momentum. But this is the analysis as it should be done. Okay? But it's just a collision with rotation. So you just got to make sure you can correctly implement that the angular momentum before is equal to that after. Question?
So, because the rod is swinging like in an actual radial way.
No, no, this way. Right. Okay. Remember the apparatus? Think of the actual lab apparatus we use. This way. Okay. Right, this way. Not this way. Okay. 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 All right. Lab exam. Make sure that's on your schedule. Obviously, we'll meet again on Wednesday, and sometime tomorrow I'll be sending you a lecture video. We're going to jump to chapter 15 and start talking about oscillations. Okay. You're welcome.